A little while ago, we talked about how useful graphs can be for understanding physical relationships and data, and this is especially true for analysing the motion of objects. There are a few different ways that we can do this, but the most straightforward one is to just plot a graph of distance, or displacement, against time, like this. This allows us to very quickly see how far something has moved, the distance, and how long it took, the time. So let's have a look at a couple of examples and learn the best way to sort of describe these graphs. So remember in our general graphs video, we said that the best way to describe a graph is to say as the x value increases, the y value does whatever it does. So we're going to do the same thing here. So let's have a look at this. As the time increases, the distance increases. So if the distance of something is increasing, that means it's moving away from, wherever the start line is. Now in this example, as the time increases, the distance is staying the same. So if the distance of something isn't changing, then obviously it must be standing still. And now finally in this example, as the time increases, the distance is decreasing. So the object must be moving back towards the observer or the origin or wherever. Nice and simple. Now, if we know how far something has moved and how long it took, it follows that we know how quickly it moved, because speed is just distance divided by time. So if we apply that idea to our graph, we can just divide the change in distance, which is shown by the y-axis, by the change in time, which is shown by the x-axis. So this is the gradient of the line. Change in y values divided by change in x values, distance divided by time. That's the gradient of the slope. So when you've got a distance time graph, the gradient is always going to tell you the speed of the object. The steeper it gets, the more distance is being covered in a shorter time, so the faster it's moving. There's another useful type of graph we can use to analyse the motion of an object, a velocity time graph. So this time we're looking at how fast an object is moving over the course of its journey and how it changes over time. Let's just dive into a few examples for this one. So here I can see that as the time increases, the velocity remains constant. If something has a constant velocity that isn't zero, then it's moving. So unlike with our distance time graphs, a flat line on a velocity time graph doesn't necessarily mean that the object is stationary. You can see that this object is moving at 5 meters per second the entire journey, all the way along. As the time increases, 5 meters per second, 5 meters per second, 5 meters per second. So it's moving at a constant velocity. But in this example, however, as the time increases, the velocity remains at zero. So this time, the object is stationary. It's not moving at all. Its velocity is zero for the entire time. If something's got zero velocity, it's got no speed, it's not moving at all. Now this example is a little bit more complicated, but it's not too bad. We can see that the object starts off with a velocity of zero. So at the very beginning, it's not moving. But then as time increases, the velocity increases. So the object is getting faster and faster. It's accelerating. However, here at the 10-second mark, as the time continues to increase, the velocity is now decreasing. So the object is slowing down or decelerating until we get to about 20 seconds when the velocity reaches zero again. So the object then comes to a stop once again. Now, if we calculate the gradient of a velocity time graph by dividing the change in y values by the change in x values, we are then doing the change in velocity divided by the change in time. And that's the formula for acceleration. So when you've got a velocity time graph, the gradient is always going to tell you the acceleration of the object. This can get a little bit tricky when you're trying to describe the motion of an object with a confusing velocity time graph. Especially with graphs that aren't straight, like this one. So here I can see that the gradient is getting less steep as the time increases. That means that the acceleration is getting smaller. However, one trap that people always fall into is they'll look at a graph like this and say, this object is slowing down, it's decelerating. But that's not true, because if you look, as the time increases, the velocity is always increasing. The velocity is always getting higher and higher and higher and higher. It's just that the steepness of it is getting less. So the velocity is always increasing, this object is always accelerating, but the acceleration itself is getting less as time goes on. The gradient is getting less steep, so the acceleration is getting less, but it's always accelerating. There's no clever trick to any of this, but I'm confident that if you just take your time, read the graph slowly, and just say exactly what you're looking at, you'll be good to go. There's one other little trick as well that I should mention though. You can actually work out the total distance that something has travelled from a velocity time graph. All you've got to do is find the area underneath the line. So for example, for this graph, to work out the total distance, I just find the area of that shape there. I'm not going to go into detail about why that works. It's actually calculus. So if you want to do A-level maths, you'll start to learn about that. But it's just a nice simple trick. The area underneath a velocity time graph will give you the total distance travelled. So if you can remember that, it's another nice little thing that you can do with velocity time graphs. Oh, all right, well, that was a bit of an intense video, but I hope you found it helpful. Please make sure to practice some questions on this topic if you're not feeling confident. That's the best way to master anything. I'll see you next time.